Perception, Chapter 2. Kind of an interesting chapter. There's a lot of theory in here, and we'll try to cover it as best we can. So let's go ahead and get started. Nice slides. Perception is a subjective experience we get from the information coming from our sense organs. Now, perception, it has to do with interpretation of our senses coming in. So you need to understand the difference between sensation and perception. Sensation is the raw senses coming in. It's everything coming in. It's everything you hear, everything you feel, everything you smell, everything you taste, everything you see, all at one time. Those are all sensations. But your perception is what you are attending to, what you're paying attention to. We detect sights, sounds, smells, taste, and tactile information from the world around us, and we sometimes recognize objects and make decisions about how we're going to interact with them. Our perception of the world is something we often tend to take for granted, as it all seems so simple, until you try to work out how the process of perception operates. There are many theories of perception, and they can appear to be quite different and even sometimes contradictory. It is possible that some theories are right and other theories are wrong, but it is more likely that the various theories are just looking at different aspects of a very complicated process. And this seems to be the way it is with perception. So we're going to get a lot of theories. We're going to talk about a lot of theories. And you can't really say that one theory is right and one theory is wrong. Usually, all theories have something right about them, whether they get the entire picture correct or not. The human eye is a remarkably simple imaging system with only two optical elements, the cornea and the lens. Given that your mobile phone may well have 5 or 6 optical elements, this gives you an idea of how optically simple the eye is. If the optical performance of your phone camera was similar to that of the human eye, you would probably take the phone back. What the eye does have, however, is some truly impressive post-processing. Light entering the eye is focused in normal vision on the retina and the light-sensitive array at the back of the eye. Most of the focusing is not done by the lens, as you might expect, but by the cornea. The cornea is responsible for about 2/3 of the focusing power of the eye, with the lens doing the fine-tuning. Because the eye is such a simple optical system, the image on the retina is inverted, something that the post-processing will cope with effortlessly. The retina contains 2 imaging systems, with each system having distinct receptors. The two, go away, there we go. The 2 broad categories of light receptor are rods and cones. The rods are the most sensitive receptors, and they handle vision in low light, being overwhelmed in bright light. The cones are the opposite. They provide daylight vision and are not sensitive to low light levels. The cones are further subdivided into 3 types, maximally sensitive to different wavelengths of light that we label red, green, and blue. And these are the 3 cones right here, blue, green, and red. These receptors then feed into 2 opponent color channels, one of which can signal blue or yellow and the other red or green. This is why we can never see a color you would describe as blue-yellow or red-green, but you can have blue-red, which is purple, or yellow-green, which is chartreuse. And this happens to be a plant with purple flowers and chartreuse leaves. That's the color of chartreuse. It's not Kelly green, it's not vibrant green. It is a cross between yellow and green. Chartreuse. At low light levels, only the rods are operating, so humans cannot discriminate color in low light. This is why blue flowers appear more vibrant at dusk. The change in the overall sensitivity of the eye going from high to low light levels is a change from the maximal green-yellow sensitivity of the cones to the maximal green-blue sensitivity of the rods. The change in the overall sensitivity of the eye going from high to low light levels is referred to as the Purkinje Effect. Purkinje was an individual that was the first one to identify um, these neurons in the eye, Purkinje. James J. Gibson in 1972 proposed that perception should be considered in terms of how it allows us to interact with the world we live in, an ecological approach. Our visual system has evolved to fit the world we live in. In the theories of Gibson, there is a strong link between perception and action, with perception being referred to as direct. The basis of direct perception is that the sensory information available in the environment is so rich that it provides sufficient information to allow a person to move around and interact with the environment without the need for any top-down processing. Now, one of the things that I explained to you before was that I started studying psychology in 1976. Well, one of the things we're going to discover is that all of these theories came in after I started studying psychology, and they came in as theories, and then eventually they were proven, or they were partially proven or partially disproven. And this is one of the reasons why when I see these theories coming in, when I saw these theories first coming in, since there was no proof that any of them made any of them were real, that's one of the reasons why I tend to argue with the theories. I'm not going to do that. This is cognitive psychology. These are all parts of what makes up cognitive psychology today. The ideas from the past, the ones that were just theories before that now we have shown are fairly accurate. These are the ones that are being presented, and James J. Gibson was one of them. A key insight in Gibson's theories is the notion that some aspects of the world are invariant, and we have evolved to exploit these invariants. If light from a particular direction falls on an object of a particular shape and surface texture, the shadows and shading around that object will always be the same, and this is known as a structural invariant. And that's why when you look at your car, go outside and you look at your car, it always looks the same. It will look the same no matter how the light is falling on it. You will always, because part of what's going on is that you're remembering what it looks like, whether it's dark. You know that you can't see the back bumper, that the back bumper is still there. It still has wheels on it, even though they may be in the dark. And that's known as structural invariant. As we move through the world, the image of the world that we perceive will flow past us, and this is known as optic flow. And you can do this just by walking through your house. That's optic flow. You're seeing everything that is going on in your house, even if something has changed. The basic nature of that flow and the way that it changes is transformational invariant. Of course, that would be transformational invariant with something that you know would be different from transformational invariant from something that you don't have very much experience with. If we move in a certain way, the optic flow will move in a way predictable from that movement. Being able to tap into these invariants allows us to act within the world. Because we're walking down the sidewalk and we're looking down and we're looking up and we're seeing everything to the side, this allows us to function in the world. Perceiving optic flow allows us to judge how fast we're moving and helps us to avoid running into things. When driving, as you approach an obstacle in the road, the closer you get, the bigger it appears. The rate of change is referred to as tau, and that, of course, is a Greek letter. So the Mercedes is braking, and so the bus behind him has to brake. And because he understands his brakes and he understands that he needs to slow down, the bus driver is able to stop before he hits the Mercedes. The issue of how objects are defined was central to the theories developed by the Gestalt approach. The key issue addressed by the Gestalt psychologists was the way that we might segregate the world into figures and the background against which they appear. And of course, optical illusions that deal with background and different colors, black and white, looking at the background. Do you look at the background? Do you look at the foreground? In this case, we have a gorilla and a lion, and they are they are blocking out a tree so that we can see the tree. Now, we don't have to see the lion, we don't have to see the gorilla. We can just see the tree with the birds, all the black background, if we like. Okay, a key issue addressed by the Gestalt psychologist was the way that we might segregate the world into figures and the background against which they appear. If we are to recognize objects, we need to be able to tell them apart from everything else. The sensory input is always the same. The pattern of light falling on the retina of the eye is the same, but it can be segregated into figure and ground in different ways. Being able to see the same stimulus in more than one way demonstrates the influence on perception that organizing things into figure and ground can have. And of course, we can see this is a lady, and she's holding a gun. Looks like she's cocking the gun. This is a hand. The black background this is a hand. This is a man's face. Not sure what that's supposed to be. Maybe a seal. Throughout the 20th century, various researchers have attempted to explain visual perception and were able to get the idea almost right. For example, Gibson's explanation for perceptive attention dealt mostly with use, while we will all attend to stimuli that we do and will not use. With use, while we all attend to stimuli that we do and will not use. So we have a lot of stimuli coming in, but we only attend to some of it. Gestalt uses the laws of perceptual organization that doesn't explain how we select the entities that we are paying attention to. So the question is, why do we pay attention to what we pay attention to? Can we pay attention to everything? Can we pay attention to smells, taste, touch, and sight and hearing all at the same time? And the answer is kind of. Gestalt theory referred to features, elements of a scene that can be extracted and then used to build up a perception of the scene as a whole. Theories that were developed to explain the process of putting a scene together sought to explain feature extraction. One such theory was Selfridge's Pandemonium model. It was a model that was developed in 1959 that purported that the eye has feature detectors that focus on select aspects of the sight and pick out the feature, the lines, the curves, the select colors, and this creates a cascade of more and more complex visions as the various features fall into place, kind of like the barn that the Amish farmers are putting together here. Recent research has confirmed that there are cells in the brain that respond to select features like spots, lines, and colors. And that's according to Haynes and Reese in 2005. So here we have Selfridge, who came up with his Pandemonium model in 1959, and it was proven in 2005 that he was correct, that there are features that we're looking at, that things do, we see things as simple structures initially, and then we add, as the features come together, then our understanding of what we're looking at increases, just like this bar. In 1982, Marr proposed the computational theory, where objects are viewed and understood in ever-expanding visual understanding. The first stage involves recognizing simple shapes like circles and lines, and this he called the raw primal sketch. The second stage, where features like borders are added, but the entire picture isn't visualized, is the 2.5 dimensional sketch. The final visual picture is the 3D sketch. And that's kind of what we're looking at here. The man drawing his own hand. There we go. Anyway, so we have sketches. So we start out with maybe a circle and maybe a line. And as things get filled in, then we have a better idea of what it is. And then finally, when we determine what we're looking at, that's the 3D sketch. And that's according to Marr in 1982. Vision uses template matching to recognize objects, where templates are stored representations of objects enabling object recognition. If we are using template matching to recognize objects, it seems reasonable that there should be regions of the brain that respond to particular objects. One of the first specialized areas to be confirmed was the fusiform face area, the FFA, and this was confirmed by Nancy Kanwisher and her colleagues in 1997, that responded particularly to face, the FFA, the fusiform face area. So from this, we understand that there are templates that we use. So when we're looking at somebody's face, we have a template as to what we're seeing. There's also evidence of regions that respond to places, and this was determined by Epstein and Kanwisher in 1998, and bodies, Downing et al. In 2001. It appears to be the case that not every class of object gets its own brain region. Some regions plainly multitask, and this was determined by Fedorenko et al. In 2013. Now, if you think about it, you're going, oh, that was 9 years ago. Wow, that was a long time ago. But the way I see it, since I started studying psychology in 1975, actually, 1975, 2013 isn't that long ago, not when you add up everything that I've seen and all the theories that I've read through the years. And they're only including the theories that are correct. There were a lot of theories that didn't quite hit the mark. This, Kanwisher's did, this fusiform face area, she was right on target. There are templates. We do have templates in our mind. Now we understand. Now we have proven this. But of course, how many people came along and said other things other than templates before Kanwisher proved it in 1997? And of course, we're thinking, oh, this is the area that identifies faces. Well, the reality is it not only identifies faces, but it does other things as well. It discriminates between one thing and another, between one car and another. So if you see a car driving down the road and you look at it and you say, oh, that's a Chevy. That's the way Chevys are put together. Or you see a SUV and you say, oh, that's a Ford Escape. That's different from a Ford Bronco or I don't know, a Ford Fusion or whatever. Anyway, so we're able to do that. Around here, we've got lots of birds. My wife likes to feed the birds. So when I see one, I like to try to identify it. Robins are easy. They're robin redbreast. They're brown on the back and orange in the front. Cardinals are easy. You can tell a cardinal from a mile away because they're red, and there are no other red birds. Around here we have trumpeter swans. Well, swans kind of look like geese, except swans are white. Geese are brown and gray. And so it's easy to tell a swan from a goose because a swan has a longer neck, for one thing, and they're white. Okay, so that's one of the things that your FFA is doing, your fusiform face area, is not only identifying faces, it can also discriminate between one thing and the other. Are faces recognized as a whole? Is this template matching, or as a sum of a number of features? For example, the eyes, the nose, and the mouth. The answer is that the face recognition appears to be a mixture of both. And that's according to research that was done in 2009 by Jagadish. A study by Frywald et al. In 2009 found a group of cells in the monkey temporal lobe that functioned as facial feature detectors, but only if the features were represented as part of a whole face. I was going to put a monkey in here, or I was going to put a person's face in here, but Jim Carrey, I found this GIF of Jim Carrey making a goofy face, and I thought that fit. I'm not exactly sure if the FFA would identify Jim Carrey, but obviously I identify Jim Carrey. One way of getting around the problem of needing an almost infinite number of detector cells in the brain is provided by parallel distributed processing, or PDP models. PDP models are sometimes referred to as connectionist or neural network models. In some ways, PDP models are still template approaches, but the templates are more flexible, and as they represent stored knowledge, they are another conceptualization of the schema. An object is represented not by the activity of a single cell, but by a pattern of activity across many cells. The key point, however, is that any one cell can form a part of many different networks. The connections between cells are as important as the cells themselves. This is why it is perfectly possible for a particular region of the brain to be involved in several different processes or in recognizing different kinds of objects. Parallel distributed processing stimuli are represented in the brain not by single neurons, but by networks of neurons. And this will get you, let me see if I'm sorry. Okay, I have to go back. Let me see if I can stop it. No, I can't. Well, let's go forward. The notion that the object recognition process is adaptive, i.e., it can learn, is an important one, as without learning it would be impossible to recognize new objects. Learning implies stored knowledge, and this is something that most of the theories thus mentioned have not addressed in detail. One problem with the theories that we have seen is that they basically emphasize top-down processing, and the interpreting the outside world means recognizing outside stimulus, bottom-up processing. As we wander through the world, the stimuli is coming to us. Therefore, it is bottom-up processing. The stimuli comes in, and we have to decide what it is. What all the theories are talking about is the fact that we have this intellectual capability of interpreting what's going on. So they're talking about the way that you figure out what something is, but the reality is this information is coming, it's bottom up, coming to you from the environment, and you have to react to it. So they're not really dealing with the entire process of consciousness. They're dealing with how you interpret what's going on. Now, maybe you feel that that's the most important, but the reality is, how do we respond to things? Richard Gregory in 1997 identified 3 sources of visual illusions, cases in which perception of the world is distorted in some way. Illusions that arise from the physical properties of the world, and this would include the ground process. Do you look at the background, or do you look at the foreground? That's a physical properties of the world illusion. Illusions that arise largely from the cognitive processes of the mind, you fooling yourself into seeing something that's not there. Illusions that are really nothing to do with the sensory processes. These include such things as rainbows and mirages. They arise from physics, not from perception. It doesn't have to do with your perception. It has to do with the physics of the world. There are illusions that arise from basic properties of the perceptual system, but are really not influenced by cognitive processes. This is a Hermann grid, where the illusory spots at the intersections are supposedly due to the lateral connections between cells in the retina, with no top-down influences. And this is what we were talking about before. This is the first type of illusion, the physical properties of the world. This has nothing to do with the way your brain is processing the information. It has to do with the way this is put together. The most interesting illusions are those that are generated as a result of top-down influences on perception. These illusions provide strong evidence for the notion that what we know affects what we perceive. One of the best known illusions of this type is the Mueller-Lyer illusion. The 2 vertical lines are actually the same length, of course, but the one on the left is perceived as being longer. The theories discussed so far cannot easily explain such an effect without reference to top-down influencing. In other words, it's your brain that's telling you that this one's shorter and that this one's longer. The reality is, if we measured them out, we would find that each line is exactly the same length. But it's your brain that's telling you that. That's the cognitive illusion. Our square world on perception influences the organization inside our brains. In the Ames room, the two identical figures in the room appear to be of vastly different size. In this case, they're actually the same person. The room is distorted so that from one viewpoint it appears to be a normal square room. In reality, one corner is much further away than the other. Based on what we know about rooms, we judge both as the same distance away, and there is no rescaling to maintain size constancy. Thus, the figure that projects the smaller image on the retina appears to be smaller. And there you go. So we have a lady who is not only really tall, but we have a lady that is really short. And it is it's a total optical illusion. Sensation and perception lie at the opposite ends of the visual process. Sensation is considered to be the raw, bottom-up input from the senses, and perception the end result modified by the post-processing of the sensors. The individual may or may not be consciously aware of the perception arising from incoming sensory information. It is possible that not all the information that is sensed will reach perception at all. Some of the sensory information entering the visual system may be filtered out by attentional processes and not form a part of our perception. The philosopher Immanuel Kant refers to the objects of events that exist independently of the senses as noumena, and our experience of those objects and events as phenomena. Kant argued that we can never truly access noumena, only phenomena. That is, we can never know the world as it truly is. Only our perception of it after it has been filtered and modified by our senses and cognitive processes. There is a saying that is often attributed to Kant, which sums up perception. We see things not as they are, but as we are. And that is Immanuel Kant. He was Danish. The visual system may sense light reflected from an object, but the light from the object and the light from the background may be too similar to distinguish one from the other. This is a problem that I have sometimes driving down the road. These days, a lot of cars are gray and silver. By golly, what color is our roads? Our roads are gray and silver. So sometimes, especially on cloudy days when you can't see the light reflecting off of the top of the car, a lot of times those cars moving down the road are camouflaged. They're gray, the road is gray. My wife and I decided when we were moving to Montana, it's so dangerous up there, a lot of times people get snowed in, and for that reason, we decided that we weren't going to buy a white car. We were going to buy a car that people could see. But the problem is, you can't buy a brown car because the ground is brown up there. You can't buy a green car because there's, some fields and whatnot that are green. So the only color that we could come up with that we were sure that people would see is red. Because there's not that much stuff out in nature that is red. So we were worried, and maybe we shouldn't have been, but we were worried that maybe we'd get stuck in the snow. If we had a white car, nobody'd ever see us. If we were driving down the road in the summertime, potentially people wouldn't see us because the road is gray, the ground is brown, the trees are green. So we bought a red car, and that was the reason why we did it. For example, a pedestrian at night can be extremely difficult for a driver to pick out from the background because of the lack of contrast between the pedestrian and the background against which they are seen. And this is a really serious problem that I have in Chin-Lee. I really hate to drive there at night, not because I can't see, but I can't see people. A lot of people on the Navajo Nation wear gray and black. It seems to be two very popular colors. And for that reason, when they're walking around, one night, this guy was crossing the street. The lights are really bad in Chinle. He was crossing the street, and the only reason I was able to pick him out of the background was because he had reflectors on his shoes. That's all I saw, the reflectors on his shoes. I couldn't see him. He had a hoodie, and the hoodie was pulled, a black hoodie. He had black pants on. He had the hood pulled up over his face. The only thing I saw were the reflectors on his shoes. And the reflectors weren't very big, let me tell you, but I picked them out. It's the same problem that you have at night with deer. So they're really hard to see. The only part that is reflective is their eyes. So hopefully they're looking at you, and if you see their eyes and you're thinking, well, there might be deer along here, then of course you can slow down and not take them out, or them take you out. The term used to describe how easily an object can be detected by the senses is sensory conspicuity, and that's conspicuous. That's a word that comes from conspicuous, and refers to the intrinsic properties of an object, such as shape, color, brightness, amount of noise that it is making, that are likely to be registered usually as a result of increasing contrast with the background. A pedestrian can often increase their sensory conspicuity by carrying a light or wearing reflective material. Motorcycles used to be really bad. Motorcycles became really popular in the 1960s and 1970s. Everybody was driving a motorcycle. The problem was that we had never seen anything like this before. If you drove on the road, of course, you saw a lot of headlights, but headlights always come in twos. There for a while, they passed a law where you had to have three headlights, so people would put one between the two headlights, a small light. Why they did that, I can't really remember. But it was really kind of an odd time. This is back in the 70s. But a lot of motorcycles were being hit. Now, part of the problem is because you were used to seeing two headlights coming at you or a mass coming at you. A lot of times the motorcycles were totally camouflaged. You couldn't see them at all. And for that reason, a lot of people on motorcycles got hit by cars. Or people just pulled out in front of them because they couldn't see them. This was a really serious problem. Back then, of course, motorcycles were smaller than they are today. Now you have Harley Davidsons that are huge, weigh a couple hundred pounds. I can remember seeing street bikes back in the 60s and 70s that probably weighed 50, 60, 70 pounds. And they were street ready. The problem was that they didn't have a very big light, and they didn't have much mass. So picking them out of what you were looking at was really, really difficult. So motorcycle riders had a real serious problem. It's one of the reasons why they had the advertisement program where they tried to get you to see motorcycles. Well, as you're driving down the road and you're listening to your music and you're looking to the left and you're looking for a car, if you see a single headlight or even, and the biggest problem that motorcycles had was that their headlight wasn't very bright. And it was certainly not as bright as a car headlight. Had to do with the electrical system. They didn't want to waste that much electricity, didn't want to waste that much gasoline. Nobody had really thought about it until the motorcycles started getting picked off. So then they made the headlights bigger. The motorcycle riders didn't like that. They didn't feel like they needed it. The other people needed to watch out for them. They couldn't anticipate what was happening. And it got into a big fight. And of course, that had a lot to do with all the arguments going on with the social arguments going on. Anyway, eventually they started putting brighter headlights on motorcycles. Now there's more than one. A lot of motorcycles have 2, 3, 4, or 5 headlights, which I think is a really good idea because personally I have a really hard time picking up a motorcycle up out of traffic or whatever. If it's coming down the road, I'm trying to turn onto a road, and I look to my left and I look to my right. A lot of times I don't see motorcycles at all. They don't have enough mass. The light's not bright enough. It just doesn't register. Sensory conspicuity may not always be sufficient for an individual to become aware of that object and take action to avoid it. And of course, that's what I'm talking about with motorcycles. Cole and Hughes in 1984 suggest that in order to be able to conspicuously perceive and to react to an object, it should also have high attention conspicuity. Attention conspicuity refers to the fact that to perceive something, the individual's senses need to detect that it is there. The individual has to attend to the information provided by the senses. Broadly speaking, sensory conspicuity relies primarily on bottom-up processing, whereas attention conspicuity is more heavily influenced by top-down processes. One of the problems, motorcycles riding around in the cities at night are almost impossible to see with all the neon lights and flashing lights and whatnot. Motorcycles are really, really tough to see. So there for a while, motorcycles were not going out at night. You very rarely saw them going out at night. And it's because they weren't bright enough and they weren't conspicuous enough for people to see. A lot of people were being hit at night. One of the theories of perception which deals explicitly with why we make so much use of stored knowledge is the Constructivist Theory, which was initially proposed by Irvin Rock in 1977 and Richard Gregory in 1980. It is called a Constructivist Theory because it is based on the notion that it is necessary for us to construct our perception of what we see from incomplete sensory information. We use what we already know to fill in gaps and to interpret sensory information. In order to do this, Gregory suggests that we act as scientists, generating perceptual hypotheses, predictions, about what we may be seeing and testing those hypotheses against the sensory information coming in. Now, this is really kind of an interesting picture. I found this GIF. This is MoGraph, has to do with cloning structures in cartooning. And so if you look at all three of these women, they're exactly, they have changed different aspects of them. But the reason they can march along like this is because they are clones of each other. And they just changed the hairstyle and the clothing style. So, MoGraph is what that's called. I had no idea. I'd never heard of it before. But I found this. And then I had to figure out, well, ladies in MoGraph, what are they talking about? As we have already seen, the end result of the perceptual process may be wrong, as with the Mueller-Lyer illusion. Gregory has demonstrated that we can perhaps learn as much about the perceptual processes when things go wrong as when they go right. When things go wrong, it seems to be previous knowledge that is to blame. And now we know how to learn things. We just scoop the knowledge off the page and we throw it in our heads. There we go. Wow, I had no idea. I didn't know it was that easy. The sensory input is rather impoverished, and we need to construct our perception aided by what we already know to make best use of the limited information coming in. Incoming information is limited in two ways. One way is that our cognitive resources can only cope with a certain amount of incoming information, so a proportion of it is filtered out by our attentional processes. Another factor limiting the completeness of our sensory information is that our senses may not provide a full picture in the first place. And this is what we see. This is what we think we see when we're looking at these two individuals. But this is really what we're seeing. We're seeing the only things that are in focus is what we're looking at. Everything else is kind of fuzzy. But we're filling in the gaps with our own knowledge, our own feeling of what it is. Although using stored knowledge to aid in the interpretation of incoming information is likely to make object recognition better and faster, the iterative process of generating hypotheses and testing them is going to take a certain amount of time. This is not a problem if the incoming sensory information remains constant, but what happens if it changes? The hypothesis testing constructivist approach would predict that a sudden change in the visual input would disrupt processing and make it more difficult to recognize an object. And this appears to be exactly what happens. DeLillo et al. In 2000 demonstrated that changing one stimulus rapidly from another disrupted processing of the first stimulus, a process referred to as masking. Okay, so if you change the stimulus, then it masks what's happening in reality. There we go. Masking. In a masking paradigm, a second stimulus can prevent recognition of an earlier stimulus if the mask follows very soon after the presentation of the stimulus. It is not even necessary for the stimulus and mask to be at the same position in the visual field. For example, not spatially coincident. A mask that surrounds the stimulus but does not appear in the same place can be effective in blocking recognition of the target. So as we are looking at this yellow dot, this green dot, and this green dot, because these are down here, we may have a difficult time identifying the yellow dot, the green dot, the green dot, because of the red dot, the blue dot, and the red dot. So these are the targets. But if these were in if they were in the area, potentially what would happen if we had 0.5 seconds to identify this yellow dot, potentially we would be able to identify it as a yellow dot. That's masking. That's known as masking. Masking could be conceptualized as drawing attention away from the initial target stimulus so that cognitive resources are no longer allocated to processing it. Incoming sensory information, flowing bottom up, is used to generate an initial hypothesis. The accuracy of this hypothesis is then checked against the continuing sensory input using reentrant pathways flowing top-down, and the hypothesis can then be modified and rechecked. Like this is a picture of Maria Cala. Anyway, she was an artist from Mexico. Had heavy eyebrows, and sometimes it looked like she had a mustache. Anyway, so it would be really difficult to identify this from all of these flashing lights. Even very early in the system, there appear to be at least two distinct streams of information flowing back from the retina. This is according to Shapley in 1995. So it's not one mass of information, it's two streams of information. These streams are referred to as the parvocellular and magnocellular pathways, the names deriving from the relative size of the cells in the two pathways. After the visual cortex, the visual information is still maintained in two distinct streams. One stream is termed the ventral stream and leads to the inferotemporal cortex, and the other leads to the parietal cortex and is known as the dorsal stream. The ventral stream is a pathway in the brain that conveys the visual information for what an object is, also known as the what pathway. It tells you, it tries to identify it, it tries to recognize it. That's the ventral pathway. So this is the ventral pathway right here. The dorsal stream is a pathway for visual information that conveys information about the spatial location of an object. And this is the where pathway. This is the part that goes up this way. This is the dorsal pathway. I apologize for misspelling is. The A and the S are right next to each other, and I don't really type very well. And sometimes I hit the A when I think I'm hitting the S. I'm sure nobody else has that problem, only me. Anyway, that's why I misspelled this word. The ventral stream is primarily concerned with recognition and identification of the visual input, whereas the dorsal stream provides information to drive visually guided behavior, such as pointing, grasping, etc. So one has to do with movement, and the other one has to do with identification and recognition. The ventral system is better at processing fine detail. This was discovered by Brazier et al. In 1991. Whereas the dorsal system is better at processing motion. Logothesis, 1994. Although the differences are only relative, as, for example, the ventral system can still carry motion information. And why are we saying this? Because it has to identify and recognize what's going on. And if there's movement that's being seen, as with the cheetah's face, then we have to identify the motion as well. The ventral system appears to be knowledge-based, using stored representations to recognize objects, whilst the dorsal system appears to have only very short-term storage available. And this is according to Milner and Goodale in 1995. So short-term storage and long-term storage. The ventral system is attached to a long-term storage concept, and the dorsal stream is attached to short-term recognition. The dorsal system is much faster because it's not looking for as complex information, so it's a lot faster. We appear to be more conscious of ventral stream functioning than dorsal. For instance, individuals may report awareness of ventral processing while manifesting different dorsal processing. And if you look at this picture, okay, I'm going to turn back to that picture. The question is, what was the pattern on the dog's back, and how many spots were inside his pattern on his back? Sorry, had to kill a fly. And the answer is, the pattern on his back is something that looks almost like a square, and there's 4 dots inside the square. That's what I wanted you to see. The ventral system aims to recognize and identify objects and is thus object-centered. The dorsal system is driving action in relation to an object and uses a viewer-centered frame of reference. And this is according to Goodale and Milner in 1992, and Milner and Goodale in 1995. This is General Grievous. That's General Grievous taking on Obi-Wan Kenobi. It is suggested by Goodale and Milner in 1992 that the dorsal and ventral system streams act synergistically, with the dorsal stream largely concerned with perception for action and the ventral stream with perception for recognition. The function and characteristics of the two streams seem to fit with the two theories of perception outlined above, with the dorsal stream appearing Gibsonian in the way that it operates and the ventral stream as constructivist. And of course, he forgot to unplug his headphones, and he's pulling his laptop off the desk. Just as the ventral stream appears to be ideally suited for recognizing objects, so the dorsal stream appears to be well suited to detecting change in the visual world. The dorsal stream detects change in the environment, so that the ventral stream can then be brought into play to see what has changed and how. Locating horizontal or azimuth sounds, azimuth is the way you pronounce that word, is determined primarily by binaural cues, specifically time and intensity differences between stimuli reaching the left and right ear. Binaural, bi means two, neural means ears, two-ear cues. So how rapidly is the information getting to your left ear and as compared to your right ear. Interaural intensity differences are largely due to the shadowing effect of the head that keeps high-frequency sounds from reaching the far ear. So if somebody's talking to you on your right side, you hear it, your head is actually blocking it from your left ear, and you can hear it better from your right. I have a hearing loss in my right ear due to an explosion once upon a time in my life. And so I hear much better out of my left ear than my right ear. And I know this especially because if I hold a cell phone to my right ear, I don't hear nearly as well as if I hold it to my left ear. Now the problem is that you can change volumes on your cell phone. So if I have it set for my left ear, um, so that it's normal, I can barely hear it with my right ear. And if I have it set for my right ear, then when I put it to my left ear, it's extremely loud. Long wavelengths, low frequency sounds are unaffected by the head, but shorter wavelengths, high frequency sounds, are reflected back. This feature has been shown to be surprisingly useful in the evolutionary arms race between predators and prey across senses. And I suggest that you read this portion of the text. It's only a paragraph long, but it's really kind of fascinating that what is it? It's a pheasant. A pheasant a pheasant chirps at the width of the fox's head, so the fox doesn't detect it. But its mother's head is narrower, and therefore she can hear the chirping and the fox can't. And of course, this has to do with evolution. Which pheasant chicks were eaten by foxes? The ones that chirped at the wrong frequency, they were all eaten. So the ones that chirped at the right frequency, so that the fox couldn't hear them, they were the ones that survived. Isn't that fascinating? Locating vertical sounds, also known as elevation, is determined mainly by spectral cues, which are generated by the way in which the head and outer ears, the pinna, affect the frequencies in the stimulus. The pinna play an active role in the sound localization. Sound reflecting from the pinna can be used to find an indication of the elevation of a sound. Sound can also be reflected back off the torso. This is known as the shoulder bounce, giving rise to additional spectral cues. As interesting as that is, you don't think of your shoulder as being hard enough to reflect sound, but when you're wearing a big furry collar, it's more difficult to recognize sounds from up above you. As weird as that sounds. So if you're just wandering around on the beach in your bathing suit, you can hear better than if you're wandering around on the beach in the wintertime with a heavy coat on. As weird as that seems. Distance coordinate is how far a sound source is from the listener. Generally, judgments of distance for sounds within an arm's length are good. Interaural level differences is large. But as sounds get further away, distance judgment is much more difficult. And distance to faraway sounds is generally underestimated. And this is a problem, and this is one of the reasons why the farther away something gets, the more difficult it is to determine how far away it actually is. There are several mechanisms for auditory far distance judgment, which are used together to determine perception of a sound's distance. Sound level sources appear dimmer due to scattering and absorption of the sound by any intervening atmosphere. Doubling the distance of a sound source can reduce sound pressure levels by around 6 decibels outside in the open with no echoes, or to about a quarter of its original level. It is difficult to make a judgment of distance based on sound pressure intensity without some prior knowledge of how loud the source should appear at different distances. The listener needs, therefore, to be familiar with the sound source, for example, a voice, or be making a comparative judgment of the distance of the two identical sources. High frequencies of sound undergo more attenuation by the atmosphere than low frequencies. Sounds that are further away, therefore, become dull and muffled. So the higher pitch the sound, the more interference there is. So if you have a deep voice, it will carry over long distances much more than a high-pitched voice. Now, this is a problem that my wife has. She has a fairly high-pitched voice, and when she's yelling at the dogs, her voice gets even higher. And one of the problems is they don't hear her. They can't hear her. So I kept telling her, if you're going to yell at the dogs and they're doing something wrong and you want them to stop, you need to do it with a deep voice. And of course, my wife thought I was crazy as a loon. She thinks I'm crazy as a loon anyway. But it's just the way the world works. Motion parallax, nearby sounds appear to shift location faster than sounds that are further away. This is analogous to the visual depth cue of motion parallax, where something closer to you moves faster than something farther away, or appears to. This is actually the Doppler effect. So as things get farther and farther away, the sound gets closer and closer together. The sound waves get closer and closer together. It's known as a Doppler effect. We used to use a Doppler to try to find veins in somebody that we couldn't find veins in, and I don't think it worked very well. I was much more sensitive with my finger than the Doppler was. And some nurses, they wouldn't stick until they Dopplered somebody. They wouldn't stick try to start an IV, and they're just fishing around. Ugh, it just the Doppler can be interfered with by a lot of different things. Too much fat, bone, arteries below your vein will give off an echo, and because of that, here they are, they're sticking. They're trying to find a vein that's not actually there. What they're trying to find is the echo of the artery. This has to do with drawing blood. You guys don't really care. I could find a vein that they couldn't find because they were using the Doppler. And I'm not even sure they use the Doppler anymore, but for the longest time they were using. If you don't think somebody has a pulse, you can use a Doppler to try to find a pulse, and that works. But if you're trying to locate a vein to stick, then you get a lot of shadow reflections. Reflection is the sound that can reach the ears in two different ways. Direct sound, an uninterpreted path from source to the ear, and the indirect sound that is bounced off, reflected by objects, for example, walls or ground. As distance increases, so does the ratio of indirect to direct sound, and the change in sound quality provides a distance cue. So when we're talking about reflection, we're actually talking about the sound bouncing off of one thing, and that is telling you where something is. But it's also masking where it is, because it's now you're getting the sound from a different direction, and that's known as reflection. It's just like reflection of the sun off of a shiny surface, but this is sound, and it's bouncing off of something. Sound reflection. There you go. Localization accuracy is generally lower for elevation sources than for sources that differ in azimuth, according to Millbrooks in 1992. Listeners can localize sounds directly in front of them most accurately. The errors are average 2 to 3.5 degrees, and sounds that are off to the side and behind the head least accurately. So if somebody's behind you or to the side of you, it's far more difficult for you to determine where they are. And if you remember the movie The Bodyguard, Kevin Costner went out into the woods and he was trying to track the guy. He was trying to shoot at him, and he closed his eyes and he listened. and he knew the guy was in front of him, and so when he heard him make a sound, he fired in that direction, and he just about hit him. But of course, he was just a few degrees off, maybe 2 to 3.5 degrees off, and it hit right beside him. The differences in auditory processing result in differences in the accuracy with which the human listener can place sounds along these axes. And if it's behind you, it's far more difficult. Unlike our eyes, our ears cannot be directed to avoid registering material that we wish to ignore. In a busy setting, we are swamped with simultaneous sounds. Principles of auditory grouping can be utilized to solve this problem and help direct auditory attention to differentiate signal from noise and separate superimposed sounds. Location, sounds created by a particular source, usually come from one position in space or move in a slowly changing or continuous way. For example, a passing car. Similarity of timbre, sounds that have the same timbre are often produced by the same source. For example, similar sounding stimuli are grouped together. Similarity of frequencies, sounds that have similar frequencies are often from the same source. Temporal proximity, sounds that occur in rapid progression tend to be produced by the same source. A listener's experience and frame of mind can influence how a message is perceived. Diana Deutsch in 2003 demonstrated with phantom word illusions that people often report hearing words related to what is on their minds. From listening to recordings, listeners reported hearing new words and phrases that were not present in the original recordings. As with vision, there is an interaction of top-down and bottom-up processing. So what is happening is that you're getting a sound, and that's a bottom-up processing, but your brain, top-down processing, is trying to identify what's going on. And because of that, sometimes it creates things that aren't there. In the phantom word illusion, what we hear may be influenced by what we expect to hear. In other words, if you can hear him, that's Doogie Howser. If you can hear him say shh, then that's a phantom word illusion. 5 senses are not nearly enough to encompass the entire spectrum of information that we can detect. Dury in 2005 suggests that there are at least 21 senses, possibly a lot more. 21 senses, possibly a lot more. The sense that keeps track of the position of our body, limbs, fingers, and so on is known as proprioception, and it operates through a system of nerve cell receptors, known as proprioceptors, that allow us to ascertain the angle of our various joints. Proprioception. Kinesthesis allows us to discern how our body and limbs are moving and is a key element in such things as hand-eye coordination and is a sense that can be improved through training and practice. Kinesthesis is also what makes you nauseous on a roller coaster. Kinesthesis. And it's the fact that you can't determine where you are. It's the fact that you can't determine kinesthesis that makes you sick. Haptic perception is tactile, or touch, and kinesthetic awareness of position and movement of joints and muscles perception. Our ability to judge the position and movement of our hands seems to be quite accurate and compares well with the acuity of our visual system. There is some evidence that the brain uses the same cognitive processes to categorize natural objects, for example, a seashell, regardless of whether the object was identified visually or haptically. So haptically has to do with touch. And that is the end of the chapter. I think I did okay. So next, I'm not sure what the next chapter is. I think it's attention. So we'll see how that one goes. I have a quiz for you, so I'll put it up, and there you go. I'll talk to you next week.